Phase control, SCR phase control. We've been doing a lot with SCRs, so you know how they work, and this is a big application for them. So there's really two things we're going to look at: how we can change average AC power for things like soft starters and lights, and how we can change DC power. That's going to take a rectifier that uses SCRs, and we can change the DC voltage with that. So typically we use that to change motors speed for DC motors. So what phase control is, we're taking AC, you got to start with AC, and you're using that to make a variable DC or a variable AC. We're not doing anything to change the frequency. So here are some applications: dimmer switches, soft starters, DC motor control, in other words making DC motors run fast and slow, and DC excitation. And excitation is a fancy word for power supply, a power supply, and they're used to, when we say excitation, we mean power a coil and turn it into a magnet. So one thing we need to look at here before we dive into it too far is the idea of a triac. And a triac is just two SCRs that you are intimately familiar with, two SCRs that are put in what we call an anti-parallel configuration. And when we say anti-parallel, all we mean is they're pointing in opposite directions. So if we just had one SCR, you would call that a half-wave rectifier. But we've got this other one turned the other way, and it can catch the opposite part of the sine wave. So this thing now will let AC through, and we can change when we fire to decide how much AC goes through. Here's the drawing for it. It kind of looks like two SCRs, right? One pointing in each direction and then one gate. So here's a triac in what would be like a dimmer circuit. And so don't worry about this firing circuit. The main thing is we've got power coming in, we go through a load, we go through a triac. So this switch, if we turned it off all the time, there'd be no power to the load, but we can turn this switch on and off. We can turn this switch on for the positive part of the waveform, and then this other one on for the negative, and we can change the overall output voltage. And what does that look like? Well, it kind of looks like this. So we might turn on the SCR and let this amount of power in, and then we turn the triac. We can turn it on to catch the top and the bottom. It's not a rectifier now. It's not a rectifier. And in a soft starter, it looks something like this. We have these SCRs pointed in opposite directions, and then we're going to fire those at kind of change the firing angle to change the voltage to the motor and ramp up the voltage. And we've studied soft starting in industrial controls class, so you know a little bit about that, and this is the most common method. So here's what a soft starter looks like. You know, it's a box with electronics in it. Here's your short circuit protection through the soft starter, and you'd use the soft starter to ramp voltage up when the motor starts running at pretty close to full speed. Close the contactor, and then the soft starter's out of the picture. Okay, a little review on sine waves. Remember, this is 0 degrees, 90 degrees, 180, 270, 360, which is the same as 0, and it just repeats. So it's one revolution. However, we usually, when we talk about phase control, we think of this as 180 degrees positive, and then another 180 degrees on the negative side. So it's just always 180 for the fire. And you'll see here in a second, this drives firing angle. And then remember, the peak voltage is whatever the RMS voltage is times the peak, times this square root of 2, or 1.41. That tells you what the peak is. So like 120 volts, which would be common, has a peak of 170. It has an RMS of, it has a peak to peak of 340. And you'll see why we need to use that. Okay, what's firing angle? There's something called firing angle. It decides when, in the sine wave, we're going to turn on the triac or the SCR. So a firing angle here is 45, and we turn the switch on and let all this stuff in blue through. And another example here in red, if we T2 here is a firing angle of 90. Remember, that's just a pulse to the gate. You don't have to leave the power on. That's what this is showing, is just a pulse to the gate. This is letting half the power through. If we fire at 90 degrees, we let half in the positive part and we let half in the negative part because we got those SCRs pointing in opposite directions, or we're using a Triac. The conduction angle is just the opposite. That's down here. All it is just whatever's left over. So if we fire at 90, then we conduct for 90. If we fire at 45, we conduct for 135 degrees. So think about these. This is a bright light, right? You can really see your dinner here. That's a bright light. We're firing very early in the waveform, say maybe 10 degrees. So we're letting almost all the power through the switch. Here we're firing right at the middle, so that's kind of a half-lit deal. And this one down here, you can barely see supper. And so you probably have your mind on other things if that's what your supper table is going to look like. Now, think about this a little bit. You've probably heard lights whine or buzz a little bit when you mess with the dimmer. Well, you're turning the power off and on constantly. You know, this represents what, 16 milliseconds and change. So every 8 milliseconds, you're turning the light off and on. And so sometimes it'll respond to that by whining, or if you have, things like fluorescent electronics don't like it, so like some LED type lights won't like it. There's electronics in there, or compact fluorescent, because they don't like being switched off and on like crazy. Okay, so those were the AC possibilities, soft starters or dimmers. Couple ideas for you. Now, probably maybe even as big or bigger application is to take this SCR and use it as a rectifier and put it into a rectifier bridge, change the firing angle, change the DC voltage output, and then from that you can change the speed of a DC motor. DC motors, their speed is proportional to the voltage you apply to them. So if you want to change the speed of a DC motor, change the voltage. Want to change the voltage? Put it in a rectifier to make it DC, put it in SCR rectifier to change the overall output voltage. So the firing angle determines the average DC voltage. You fire early and you get most of the power through, and this would be a DC motor that would be humming along pretty good. Now think about this. This is the most simple example. This is the firing circuit, the diode and the resistor. But here's the SCR. And best case scenario with this, you'll only get half the power through, right? Because this will never get power going the other way. So we've immediately chopped the bottom half. And then depending on the firing angle, we can start early and get all that power and voltage through. Or we can start in the middle and just get half. Or we can start at the end and not get any. So let's look at this 90-degree firing angle. You're going to expect to get about a quarter of what you started with. If you started with 120 volts, you already lost 60 here. And then you're going to split the other 60 down in half. So you're at 30 volts would be what your voltmeter would probably read, something like 30 volts. Now on this one, if we had 120 volts going in, we might be able to get, on average, about 120 volts DC output, and depending on when we fire it, if we fire it halfway, we'd get half voltage. Here pretty early, right, we're getting most of the voltage through. Who knows how much, 70-80%. This is a full wave rectifier, and we just put some SCRs in there and we change the firing angle to change how much voltage we are working with. Here's a three-phase one, so that's even slicker. This is what you'll see on the mining shovels. In fact, they have two of these. They have one to run the motor in the forward direction, and they got another one that's hooked up with the opposite polarity. Just flop the polarity around to run the other direction, to run maybe in reverse. So 6 SCRs. Now some of these, there's designs where you can do this with 3 diodes and 3 SCRs. But anyway, you get the basic idea of phase control. We're just changing when we turn on the gate, which then changes how much power gets through. Now here's another example. Here's an exciter. Exciter just means it's a power source that powers a coil and turns a coil into a magnet. That's what exciter is. They used to be made with DC generators. They were spinning, and back in the day, and in more modern in the last few decades, they've switched to SCRs, which instead of a big rotating DC generator, you have a static exciter. In other words, you have an exciter that's just sitting there without any moving parts. So this is a MFSE. This would be off a haul truck motor field static exciter. So it has SCRs and a rectifier bridge. And if you follow this through, it goes through and powers these coils up in the field of the DC motor. So it's taking the field of the DC motor and turning it into a battery. Into a magnet. And this is essentially a voltage supply, and you can change this voltage by changing the firing angle, which would change the strength of these magnets, which will change the speed and torque characteristics of the motor. Now, phase control can't do everything. One of the key things is that you have to start with AC. All of those examples, you started with AC. It doesn't work for DC. So this isn't going to work at home on a drill or at the golf course. It isn't gonna do anything. We're going to see that pulse width modulation is what we use to deal with those types of things. So we're going to use transistors and pulse width modulation to change speed on these guys.